Okay, thank you everybody for staying until now. It's been a pleasure to see you here and also to be invited here speaking at ComSec in Hacking the Box, again back in Dubai. So basically a few words on who I am at the moment. Sorry, Mom. Okay. Well, I actually work as a product security consultant and I mostly focus on TE, IoT, on devices, fault injection hardware, and this has been my research. Well, mobile security, exploitation access point, I broke a bit of white box cryptography, TEs and IoT, and last one was fault injection and privilege escalation on Linux. Okay, let's go to... Yeah, basically, regarding devices, often we actually buy a device and there is a brand attached to it. And we think that that's the vendor and that's the one that owns the device. Or you might even be thinking that you are the one owning the device just because you've bought it, actually. Unfortunately, that you see that the number of components that come from an iPhone X, well, it's often believed that Apple does everything from scratch. Well, it does everything from scratch with the help of different manufacturers. For example, the notable are the Broadcom chips, the baseband processor is from Qualcomm, and so on. Actually, what can be seen also from, I think that's something wrong. Okay. The Apple suppliers for 2018 are in total about 200. So if you get an iPhone X, you will get components from at least 200 different suppliers in one single phone. So basically, the main point is that this statement is actually wrong, because nobody actually really owns a device nowadays. There is no way that you can attach the responsibility of all the vulnerabilities on a device only to one single party. So this is already for understanding that a device is not only a device, it's just an ecosystem effort that gives you a product. So at first you have an IP. Let's say you have ARM. ARM does not even manufacture chips. They just sell the IP. And you have the hardware design and also the hardware security primitives which are established over there. Think about TrustZone, for example. Okay? But those are IPs. They do not exist until you make a SoC, a system on chip. And so at that point, the IPs become actually something embedded in silicon. So you will have the hardware security features. At this point, you will be establishing the basic of the TrustZone hardware security feature. You know, the famous security bit, NS bit, and all these things are established at this level. Then at this point, you will have that the SoC manufacturer will also integrate low-level software and low-level software party component. For example, this is the situation where your TE software, your TOS, will be probably integrated at this point, which might come from a different manufacturer as well. Okay, and then at this point you will go through the OEM and we'll go to the final products, but it will be the final PCB design. The PCB does not exist yet until you reach this stage at all. But you have already integrated in your design quite a number of different products from different manufacturers. And the point is that each component in the chain, not only each layer, but each component in the chain has its own threat model, when there is one, of course. There are use cases and also its own assumptions. So the problem is that at the boundaries of such component, there might be some assumption that may cause system-level vulnerabilities for the whole system. We're going to have a few examples of these assumptions. Excuse me. There is something. Okay. So basically, out of my experience, I had the luck of seeing a few classes of these assumptions, and I just want to share some with you in terms of actually classes. Okay. There is an assumption which I call an assumption of completeness. Let's put it this way. So basically, what's happening is that when we look at a component, either hardware or software, we assume that, well, it may be assumed, not necessarily we, or you, but it may be assumed that when you look at this component, that the information that you have regarding this component is sufficient for understanding its impact in the system. And this is a quite strong assumption. This means that you can evaluate components in isolation, either software or hardware, and you will know how they will going to behave in the system. Okay, let's have at least one example that my clear a bit the understanding here. Note that this assumption may apply both to design, so that when you integrate a component, but also during testing. So you assume that you can look at the subsystem in isolation and then being able to predict what is going to happen at the system level. Okay, let's do a brief software security assessment together. We take a string compare implementation. It's taken from an open source, usually BNG. It's the latest version, and the full source code is available. So basically, you have everything, right? Let's see if we can understand what we can do here. So, do you see any vulnerability here? I don't see any buffer. There are pointers to external data. I would say that if you think about only software attacks, such as the usual logical attacks, to my knowledge, this is not vulnerable. You will not be able to find a vulnerability which is related to the typical memory corruption or even logical. I mean, this should be safe. Okay. But then there is another point. Let's assume that these may tell you something does tell something to anybody, this one? Do you see anything here now? Well, the problem is that there is an early termination, so as soon as you find a different character, you will just stop. So this means that this is prone to a timing attack. Meaning that the string that you compare will not always be checked, but it will stop at the first wrong character. So you will know when the character is correct or not. And this means that if you were able to access a measurable channel, such as you can access the timing, and be able to sample with sufficient precision, I'm not talking about scopes only, I'm talking about something which you will see in a moment. And if the quantity that you are comparing now is a relevant asset, like a password or a MAC, then this is bringing a vulnerability. So basically, depending on which highs you use in order to look at this code, it may be either vulnerable or not, or actually may bring a vulnerability in the system or not. Because what you are seeing here is that the precondition for making these dangerous are not in the code. They are in the system. So basically, the point is that we are now with the software components, that if we consider only software logical attacks, well, the system is not vulnerable, there's no problem. But if the system has a different threat model that includes not only the software but also the timing attack, then this becomes vulnerable. The point is that you're looking at the code, you have no information where this is going to be used. What do you decide? What do you report? Because you're looking at the code in isolation. Okay. So the problem is that we might have, in some situation, a component, either software or hardware, which is judged secure according to a threat model. Then we have a system, again, that, that is designed in order to withstand both software and timing attacks by design, and that is regarded secure. Then you put them together, and then what happens is that from two secure components, you get a vulnerable system. Because you might be able to exploit the timing vulnerabilities that is brought by the string compare, basically, which has been judged secure only because a different threat model has been used. So basically, the component level information, so the code, what information you have in the code is not sufficient for establishing if you are introducing a vulnerability in the system or not. Because it cannot be, this vulnerability specifically cannot be assessed only at the component level, because it depends on the final system threat model. If your threat model does not include timing attack, so that the final system doesn't care about those kind of attacks, then there is no vulnerability. But if the system can be attacked by using timing attack, then this immediately becomes a vulnerable path. The problem is that code review does not solve the problem. You can review that as much as you want, unless you have additional information on the final system and on the threat model, which is relevant. So basically, if I review this code, I should give you the information that depending on the threat model, this might bring you some vulnerabilities, and only the next stage that is integrating this code can decide if this is actually a problem or not. But people reviewing this code or writing this code, if they are not concerned with the other threat model, well, the piece of software is perfectly fine. Okay. Regarding the exploitability, well, it's a string comparison, so perhaps many people will think that this is not relevant. Well, it's for sure regarded in practical by research in the vast majority of cases. I mean, but the vast majority of cases which have been explored are actually remote server with fast CPUs, such as 3.3 gigahertz that are sitting on a LAN or a remote LAN. And that's actually impractical because in those cases, one single instruction is below 1 nanosecond. That's what we're talking about here. So the point is that how do we remotely measure 1 nanosecond of difference for an instruction? Well, for a loop, you might be a bit more. You maybe have 10 or 20 nanoseconds. So this is actually impractical, but we are now in a world where 50% of the traffic is made by machine-to-machine traffic. We have IoT almost everywhere, which systems are much slower. So basically, you might have the typical Arduino might go from the 16 megahertz level of the Arduino Uno, or you might have an SPU32 going at, I think, 250 megahertz, if I remember correctly, 240. So this is much slower than 3 gigahertz. Completely. So the point is that, in fact, one savvy paper writer said that the timing attack on regular string comparison have to be assumed feasible for any embedded system at the moment. That is still actually true. And the reason is that I should have been demonstrating this, but unfortunately I don't have the time. But if you take an Arduino Uno with 16 megahertz and 100 megabit, and you have a pin of 8 digits. 8 digits is about basically 10 digits to the power 8, so it was a 100 millions combination if you want to actually brute force that. It goes down to 50 millions if you take into account the brute force approach, okay? But basically by measuring the time, you can actually see that I'm able to retrieve the pin in just 68,000 checks. Basically, I just explored the 0.07% of the brute force space, and I was able to retrieve the full pin. As I said, I am not able to do the demo here due to time constraints, but the demo will be available tomorrow at the Hack in the Box Armory, HITB Armory, where I'll be able to demonstrate the impact of this kind of attacks. I will do with a framework which I'm researching and working with. So this is a basis for new research on remote timing attacks on IoT devices. So the point is that, as you've seen, even the exploitability now really depends on where you put this code. Because if you put that on a full, a very fast remote server, well, there is no way you can exploit the string comparison. But if you use the same code on a different device, which is an IoT, then again, this becomes exploitable. So even the exploitability cannot be established by looking at code. So we are looking at the code that we are very good expert in software security, in hardware security. We have all the information available regarding the code, but we are not able to assess if it's vulnerable, if it brings a vulnerability in the system, or if it brings exploitability to the system. So basically, I would say that the assumption that you look at components and that you know about the system is actually failing. Okay, how can we help this? Well, basically, when you actually receive and include a component, either a software or hardware component, you should always ask for a threat model. Someone has designed it with something in mind. We'll give an example in the next slide. And you should always ask. It's a simple question, but in my experience, I rarely do see that asked. The second thing which I don't see asked is that, well, you develop this component, either hardware or software, which are your security processes? Do you have SDLC? Do you do design reviews? Do you do source code audits? You do perform product penetration testing? You're buying the components, so these are legit questions to ask. Second kind of questions which I usually don't see asked. The third kind of questions is that, okay, this is more for final products. What are your in-field security processes? So how long does it take for you to release a fix in average? Do you have metrics? Well, we don't. Well, but I'm asking, you should. Then, what is the security maintenance? How long are you giving the firmware update for? And firmware update does not mean router. It might mean the fingerprint sensors on this phone. This is what we're talking about here when we talk about components. So basically, and if there is a process behind which is serious, they should probably do the security evaluation. And you can ask the security evaluation report. Because the point is that when you're buying a component, you're also buying its risk. It's included. So if you're buying its risk, you should also get a security report, right? If you are security concerned. If you are not security concerned, then probably it's a problem of someone else. So a good example instead is in case of ARM Trust Zone, where in the documentation they specify that it's an hardware enforced, so hardware support, for logical separation. So it's not an hardware defense. It is an hardware support for separating logical domains, software. In fact, they say the lab attacks are outside of the scope of the protection provided by Trust Zone technology. So if you're thinking of having a fault injection resistant system by using only Trust Zone, I think you're on the wrong track. You should redesign your assumptions. And this is a good example because they provide the threat model along with the documentation, even if you don't necessarily need to ask. Second kind of class of assumption, which I often do also see here, is that correctness. A lot of times I do see, especially software developers or software testers, there is the assumption that the system will always behave as intended by specification. Actually, the systems works on hardware, which is a state machine, which works on physics. And if the boundaries of expected, behavior are satisfied, well, perfectly fine. But if you are able to introduce fault, either by clock voltage, EM, or laser, or there are even more that they will not fit in the slide, if you're able to introduce a glitch by using a controlled environmental change, you can alter the behavior, and it's already proven that by doing this, there are chances that you can exploit this vulnerability in the hardware which has been triggered by your glitch. The first assumption that I always hear that this is expensive attack. Actually not. I would really recommend that to have a look at the presentation from my friend Rafa. Cheapskate attacking IT with less than $60. He is doing SCA and fault injection attacks with that amount of money. So that is usually an uninformed assumption. So that's why it's in this slide. There are other assumptions that usually go with fault attacks. The first one is physical access is required. It's wrong. Rowhammer and Corkscrew are software activated or software initiated fault attacks. So you are able to trigger a fault in the hardware by using software. And if you're able to do that, then you can actually do it remotely. So no, there are classes of fault attacks which do not require physical access. The second point is that usually when you think of fault attacks, you want to bypass security decision point. So something which I often hear is that, well, we don't decide anything. We always do the checks, so there is nothing to attack. Again, it's wrong, because there are new fault models which allow you to perform directly code execution. Well, also, we have countermeasure in software because we do double checks, we do random delays, so it's difficult to attack. Well, actually, it's still wrong because there is a new fault model that can completely bypass software fault injection. There is another one regarding secure boot. Well, our secure boot is encrypted. You need a key anyway. Even if you bypass something, you don't have the key. It's wrong. It's also wrong, and wait a minute, because I think I'm sharing something that might be interesting and maybe new for you. So the typical secure boot is that you have loading boot stage is loading the memory as stage add, then you are loading the signature add, and then you just do perform the signature check. And then if everything is fine, you execute the firmware directly after the verification. The text boot attack is that you use a modified boot stage, so you change it, basically. So you try to push it into the device, and where is the verified signature? Usually, it should say, hey, you're not allowed, the signature doesn't match. So the text boot attack try to glitch exactly that point in order to bypass that signature. Once in X amount of time, if the hardware is vulnerable, it might happen that for a number of reasons, which would be too long to go into at the moment, that verified signature might either give a wrong result or not be computed and so on, and depending on the call graph and other things, you might be able to have your malicious boot stage executed even if the signature is not correct. Okay. This is used called instruction skipping fault model. So you skip something that should be executed while it's not. In the encrypted secure boot, this is a bit more problematic because you have a boot stage which is encrypted. Then you have a signature, of course. Then you have a decrypt stage. So before doing anything, you need to properly decrypt that module. which makes everything quite difficult with a normal textbook attack. Because you don't have the encryption key in first place, so you are not able to create the modified boot stage in first place that if you bypass the signature, then will be properly executed, because that would be probably garbage. That is the point. Because even if you bypass the signature, you don't have the encryption key for that modified bootloader, and when you decrypt it, will probably be absolutely bogus, and you will not be able to do that. So this means that sometimes the encrypted secure boot attack secure boot is considered safe from fault injection attacks. You might need even side-channel analysis. Well, actually, this is a bit wrong now with new execution, new fault models. Well, we presented in 2016, well, I did present last year, basically, how to execute code in Linux kernel from user space by using this fault model, but let's think about it in secure boot. This is not new. This has been already, in a way, discussed briefly in previous papers, but I think this is the first time it's been, let's say, more thoroughly discussed. Let's think about for a moment only about ARM32. The program counter is directly accessible in instruction, so you can always do something like move R1 to R7 or move R1 to PC. I mean, PC can be the target register of the destination register of a move instruction. Well, basically, if you take a move or any instruction that use a destination register, you might be able to corrupt it so that the destination register is not the intended one, but program counter. So basically what's happening is that the operands that should be going to R7, for example, in the first one, will go to the PC, which will immediately trigger a different code execution path. Let's look about the LDR. So you are reading something from memory in R1 and should go into R0. Well, if you glitch and your payload is prepared sufficiently, that payload which should go into R1, for example, during a mem copy, is going to end up into PC. So interestingly, what you are copying is going to be the address where the PC is going to end up. Okay? Okay. This seems to be quite interesting. This is not theory. It has been already proven, so I'm not providing any additional... if you need paper reference, let me know. I can actually provide them. In the end, if the PC is not available, it's not addressable, you can also do the same in other architecture where the stack pointer is available, basically. And then you enable some ROP kind of exploration part. But it's clear that if you can put in the program counter whatever you want, because that's the data that is being copied at the moment, it's clear it's basically a game over. It's like that you buffer or flow without having vulnerability. Okay. So basically, if you look at now at the secure boot encryption, take a look at the payloads. The payload is done. There is a plain text payload, not an encrypted payload at the moment. And at the end, there is a sled that has a stage adder. What is stage adder? Stage adder is where the payload is being loaded. Okay? So when you actually load the payload, you are copying basically the payload in stage adder. That's where it ends. But at the end, you're also copying the stage adder address itself. And if you glitch during that point in time, then that address is going to end up in PC. Then, if the program counter is set to that address, assuming that the destination memory is executable, PC will start from stage adder. What is there at that point? There is your plain text payload at that point in time. And the point is that this is before the decryption phase, and the rest will never be executed. So basically, you are loading plain text and executing a plain text payload during an encrypted secure boot by using a different fault model. There is no instruction skipping here. This is called instruction corruption or instruction modification. And thinking along this way, you can enable a number of things which have been explored in other talks that can break a lot of assumptions. Okay, this should be... Excuse me. Yeah, okay. So that part is never executed. The problem is that fault injection vulnerabilities are located at the physical level, and they cannot be identified by any hardware or software code review. You can stare at hardware Verilog or VHDL, or even by looking at physically at the implementation or at the code, whatever you want. You will never be be able to rule out fault injection vulnerability. Similar goes for SCA, although with a bit different approach. So the only point that you can do is that testing the real implementation. So you need to actually test if the hardware is sensitive to that kind of glitching. Not necessarily doing the full attack here, but you need to understand if the hardware actually responds as you would expect. So not necessarily going through the full attack, because if it's so, this testing should be performed right after silicon integration, because this vulnerable hardware may affect entire classes of device. So want to catch it up as soon as possible, as soon as out of the factory, basically. So this is also an assumption that should be really cleared out from the mind of software developer, even hardware developers sometimes, okay? So the point is that if you have fault injection in your threat model, you should ask your SOC manufacturer for security evaluation report. Because if they don't have one, then you should assume for the worst, because they didn't consider the problem in first place. Do not rely only on hardware software audits. So if someone told you, I reviewed the code, or you're the Verilog, you said, I don't think you know enough your work. Then, so either you have a countermeasure or you're painfully and desperately vulnerable on this. This one will be faster. Consistency. The point is that the entire system seems to have, in some people's mind, only one threat model, and there is only one asset, like process separation for Linux, or other things which might be relevant in your use case. So the assumption is that across this entire mess of 200 different components and supply chain, there is only one single threat model in mind. I think there is already some problem with this kind of assumption from the start. For example, typical security model is that you have a kernel that enforces the use process separation. Nice. We keep on talking about user space and kernel exploitation for days. Good. Then you think about it when there is a TE. Is only that part. Only. You might have another kernel with an hypervisor. You might have even a TE. Good. Do I actually always, all of them help to enforce this nice process separation and user space kernel separation? Well, I'm not so sure, because in the TE security model, there, the REE, where all the things are that we actually use, are something to protect from, are not something to protect. The separation also there are more, but the point is that there is no intention to protect the REE. So this means that things like these, that the TE itself, which is completely unaware of user RE memory, could be exploited, could be leveraged from user space in order to bypass and exploit the kernel space. Because, well, in this case, the driver did not do exactly a very good job, but the TE had no way of distinguishing, it's just memory. So the point is that you might have different security models at the same time, which may not be aware of each other, which you can even use, you can one against the other. So even this one should actually be dismissed. And the recommendation is that you need to understand component security model and to evaluate them with your final system threat model, because there may be no consistency across threat models, and you should expect none. Last one is thinking that there is only one subsystem, the one that you are considering, or the one that you are developing, or the one that you are designing. People only think about that, protecting it from the typical threat model of attackers. The problem is that this is all just a simplistic model. You have a CPU and you have memory. But the reality is that here you have the CPU, here you have memory, that there are many other IPs that can access memory. So this means that whatever the CPU thinks is being separated might be not separated at all by the other guys. So this means, for example, the reason for Broadbound to work, you exploit the Wi-Fi SOC, then there is a vulnerability in there, then the Wi-Fi SOC is just see memory as memory, it doesn't care about kernel or user, it just writes to memory, and then there you modify the kernel, and then this point, basically, when the main SOC actually uses the kernel, is modified. So at this point you have a kernel code execution without even touching the main SOC. So this is quite interesting, is that the SOC are actually execution unit. You don't have one, you have many, many more. And other SOCs may have access to the same main memory where you think your security model is based upon. And then they may not be aware of each other's security model, because what is kernel user space in SOC 1 is completely addressable memory in SOC 2. So break SOC 2 and then the rest will just fall. So what could have been done? You should have been reviewing the code and testing. That's why it's very important. You should have an SMMU in the hardware design. If it's not there, there is some problems that you might have in your design. Yes, it's telling me that it's about time. And finally, you'd also need to properly configure that, usually in a TE on the boot stage layer in the main SOC. And also we are missing other execution units, DMA capable IPs, and other bus masters. All of them. So this means that basically I've seen chipset where there were in excess of 100 DMA engine in my experience. So good luck with securing that. So also this one should be dismissed. I would say that this is a quote from a movie. I would like to change this like this. And conclusion, I'm actually there. A few reflections. System security. Threat models may greatly differ between components, and the security model of the system is completely different from the sum or the security of each component. So if you look at 100 components in isolation without thinking at system level, you might have big problems. When you're doing a security evaluation, you need the context. You need the system level information for understanding what is the impact, otherwise you will not be able to assess it. And code review cannot identify all the vulnerabilities. Your design, hardware and software must cooperate across the whole system. I would have more examples, but this is not the right moment. But this should happen regardless of manufacturers or department or team's boundary. There is no point in having hardware and software teams not cooperating nowadays in someone making secure products. Really, it's like shooting yourself in your foot. You need to protect from other subsystems, not only from the external attackers, because from your point of view in defense in depth, the rest is also an attacker. So the point is that unchecked assumption can bring some problems. So my recommendation, establish a system-level threat model and apply and verify consistency everywhere across the system. And this should be done even before designing the system or starting that, or even buying something. You should have clear what you want to protect and from whom. That's and how in terms of what kind of attacks are applicable. So for every component, try to have an understanding of the use case and the threat models. And when you have a security assessment and testing, you must consider the system threat model. If you don't have one, you have a very big problem. And every time you buy something, basically ask for a threat model, security practices and processes, and a security evaluation report. Because you're already paying for it. You're just not asking, probably. Questions?
Any questions from the room?
Thank you, Cristofaro, for the very interesting talk. When you go back one slide, please. The last recommendation.
The last recommendation.
To get from for every component, the threat model, security practices and processes, and the security evaluation report. How practical do you think that is?
The point for this is not necessarily obtaining, but sufficiently creating a pressure in order to let the components and suppliers understand that this can make a difference in their product, such as establishing security as value. I would not expect that you actually receive it, but the fact that you ask for it will start making a difference between people who are going to provide you a bit more and provide you a bit less. So this would be a way of providing a model where security is a value and not only so much of a cost. So it's more an enabler and an initiator rather than having results now.
All right. Thanks.
You're welcome.
Any more questions? No. Okay, I want to thank you, Christoph, for this great talk.